Hi everyone, I'd like to welcome you all to the 13th webinar in this discussion series on tipping elements, the notion of irreversibility and abrupt changes to the Earth system. My name is Ruth Townend. I'm a research fellow specialising in climate risk and diplomacy at Chatham House. I'm currently working on final recommendations for the Cascades EU project, which looks at how climate impacts may cascade across and into Europe. And my colleague on that project, Ilona Otto, presented at a previous webinar in this series on social tipping points, tipping towards positive social change, which you can find the recording from that on the website for the series if you were unfortunate enough to miss it. In my previous role at Ipsos, I led a survey of public attitudes towards the global commons, including exploration of understanding of Earth system tipping points on behalf of the Global Commons Alliance. I'm very excited to be moderating this discussion today and looking forward to hearing from both our excellent speakers and the very accomplished and interesting attendees who I can see still joining us online now. So the goal of this discussion series is to advance knowledge on tipping elements, support efforts to increase consistency in treatment of tipping elements in the scientific community, develop a research agenda and design joint experiments and ideas for a tipping element model intercomparison project, or TIPMIP. The networks behind these series are the Earth Commission, a global team of scientists with a mission to define a safe and just corridor for people and the planet. AIMS, the Analysis, Integration and Modelling of the Earth System Project, a global research network composed of Earth system scientists and scholars that seeks to develop interdisciplinary ways to understand the complexity of the natural world and its interactions with human activities. And both AIMS and the Earth Commission are hosted by Future Earth, a global network of scientists, researchers and innovators collaborating for a more sustainable planet. Also, the Safe Landings Climate Lighthouse activity of the World Climate Research Programme, exploring routes to safe landing spaces for humans and natural systems. This event is co-organised by the International Institute for Applied Systems Analysis, the Potsdam Institute for Climate Impact Research, and the Global Systems Institute at the University of Exeter. So our focus for today is on climate tipping points, how to tip society and not the planet. Both of our speakers will present before a Q&A session, which you can all get involved in. But during their talks, feel free to post questions and indicate to whom your question is directed using the Q&A feature at the bottom of the Zoom window. Everyone can also upvote preferred questions, and we'll then get to these in a discussion session after the presentations. Following the event today, we will post the recording on the Tipping Point Series Confetti webpage, so it will be accessible to you in the future. Now, it is my pleasure to introduce our first speaker. David Armstrong McKay is a Research Impact Fellow at the University of Exeter and at the University of Exeter and Global Systems Institute, working on understanding and enhancing Earth systems and socio-ecological resilience. He completed his PhD in Ocean and Earth Science on Earth Systems Modelling of Paleoclimatic Disruptions at the National Oceanography Centre, Southampton, followed by postdocs on ecological resilience, agroecological systems and climate biosphere feedbacks at the University of Southampton and the Stockholm Resilience Centre. His research uses numerical modelling and analysis to investigate Earth system resilience in the past and the future, including climate biosphere feedbacks and tipping points, dynamics and indicators of ecological resilience, and pathways to socio-ecological systems transformation. David, thank you very much for being here. The floor is yours.
Thank you for the introduction. Hopefully you can all see my screen. Today I'm going to be talking to you about climate tipping points in particular, referring to a paper we published recently in Science back in September, but also giving you a bit of a general background around tipping points and how they might apply to the climate system. And I'm sort of introducing the negative tipping points, to which Lloyd will be talking about the hopefully positive ones that might be able to counteract some of the not so pleasant things I'll be talking about now. So just as a bit of a starting point, this is a figure from the latest IPCC report looking at the relationship between cumulative total carbon dioxide emissions over time to global warming. So on the bottom axis, you have the cumulative CO2, and on the vertical left-hand axis, you have the increase in global warming. And that black line is the historical observed warming. And you can see that there's a bit of variability on that line, but it's generally going up pretty linearly. It's a straight line. The more CO2 is being emitted to the atmosphere, the more global warming is going up. And it's a pretty simple linear relationship. If we look into the future, that's the colored lines on the right-hand side of the plot are. these are showing future emission scenarios and projections from the IPCC. The blue ones are the low emission scenarios that stay within the Paris Agreement, and the red ones are the ones where climate rules and regulations start to fall apart and we get a high emission scenario. And you can see that it's anywhere between 1.5 by 2050, going up towards 2.5. And we're probably somewhere around the middle on current trajectories. And you can see from these that warming is expected to keep on going up in a fairly predictable linear way with further cumulative CO2 emissions. It's quite a sort of predictable relationship. And this is a strong feature of the IPCC report. But having said that, at a global scale, the relationship's quite linear, but for climate impacts, and particularly on the regional scale, climate impacts may not always be steady. Sometimes you might be able to pass something we call a tipping point, which can lock in substantial non-linear changes. So what do we mean by a tipping point? Well, a simplification here is that tipping points occur when change becomes self-sustaining when a system is pushed beyond a certain threshold. An analogy I like to use here is shown in this animation of a ball being pushed up a seesaw beyond the pivot. So when you're pushing the ball up this, if you let go before you reach the pivot, the ball would roll back to where you started. It returns to its original state and it's quite resilient. But once you pass that pivot point in the middle, that threshold, the ball will keep on rolling even if you let go of it. The change in it becomes self-sustaining and it will keep on going until you get to a new state from which it's difficult to get back from. What drives this sort of behavior? Well, the main thing is these positive or amplifying feedback loops. And as an example, I'm going to be showing how this works currently in the Arctic. So there's a lot of sea ice in the Arctic. This is quite white and reflective. It reflects solar energy back from space. And that's this left-hand animation here. You can see there's solar energy coming in. When it hits the sea ice, most of its that energy is being reflected back out. That keeps that area colder than it would be otherwise. Whereas the sea surface is blue. It tends to absorb most of that energy and it heats up. So this keeps the Arctic colder than it would be otherwise. But what's happening now is that with global warming, the sea ice area is starting to reduce. The sea ice is retreating. That's increasing the amount of dark blue ocean area being exposed. More energy is being absorbed in this region than before. That increases regional warming and that helps to melt more sea ice. And this is this right-hand animation here showing a positive feedback loop where increasing warming can eventually drive a small increase in warming, can drive a bigger increase if it keeps going around this feedback loop. And this bottom map shows the actual warming being observed recently around the world. You can see most of the world is red, as you'd expect, but it's particularly red in the Arctic, around 3 to 4 times as much warming there as the global average. And that's partly because of this feedback loop. Now in the Earth system, there are plenty of negative feedbacks as well that help stabilize things. Otherwise, life probably wouldn't have emerged if the whole system was completely chaotic and unstable. Normally, this would help prevent runaway changes, but under certain conditions, you might be able to temporarily outpace these stabilizing feedbacks. And that's what happens when you reach a tipping point. Now, this is just another example to get into kind of some of the ideas and evidence we look for when we're thinking about trying to find tipping points. And this is one looking at vegetation, the relationship between vegetation and rainfall. In this plot, we have the bottom horizontal axis. From the left-hand side is wet, high precipitation. Going to the right means it's drying out. And on the vertical axis, we have the amount of vegetation, the woodiness, whether there's lots of forest or not. And the black line is showing what ecosystem type is most stable at that level of rainfall. So over here on the left-hand side, where it's really wet, you get lots of forest, as you might expect. On the right-hand side here, because there's not so much rainfall, it's very dry, you don't have so much woodland. You get more grassy savanna or bare, barren type ecosystems instead. That's what you might expect. But the interesting thing in the middle here is that there are 2 possible stable states given an interim level of rainfall. You can either have patchy vegetation or you can have not much at all. And to explain how this works, we'll go through examples starting out from the top corner, assuming we have a forested area, but it's drying out. So you start to get a decline in the amount of vegetation, but it's not as much as it could be because there's self-sustaining feedback in some of these semi-arid areas where the presence of woodland or forest actually helps to sustain itself because it's recycling moisture, it's making its own rainfall. That helps to stabilize that forest and keep it going. But there are limits to this. If you get to the point where there's just not enough trees anymore to recycle enough rainfall, you can get to a threshold beyond which this feedback no longer works, and it effectively goes into reverse. So at this point, you start losing trees, less rainfall is being recycled, that triggers more tree die-off, and that can keep on going in a process called dieback. So you drop down to this alternative stable state of not much vegetation at all. If you were to then start increasing rainfall again, you start to reverse the original climate change, you actually don't restore the forest straight away. You're going along this bottom leg here, because without any of the forest there in the first place, it's not generating that self-sustaining feedback yet. You have to get to a point where there's enough rainfall to independently make sure there's enough rain for a forest to exist. So this type of behavior is called hysteresis, where effectively, if you go past a threshold and you lock in this big change, even if you take a step back, you have to go much further back in the level of forcing in order to get your original system back. And that's one of the key features of tipping points, is locking in these really big changes that aren't easy to reverse. And this is the evidence we look for when looking for potential tipping points in the real world. Now, how does this apply to the climate system? Well, back in 2008, there was a paper by my colleague Tim Lenton and others where they tried to identify this sort of behavior in the climate system. They identified 9 parts of the climate system that they termed tipping elements, which could feature these sorts of tipping points. Since then, various other elements have been added to this list, and some have been questioned as well. And this map is just showing some of those. So the blue ones, they're in the cryosphere, the icy parts of the Earth system. So we have the Greenland and West Antarctic ice sheets, for example. We have sea ice, we have permafrost in the northern and high mountain areas as well. In the green, we have biosphere parts of the Earth system, the living parts. So we have the Amazon rainforest, which is vulnerable to that sort of dieback process I've just described. We have boreal forests, which can die back in the south and jump into the tundra in the north. And we have tropical coral reefs as well, which can, because of bleaching, can die off if they start to bleach too often. And finally, in the red, we have circulation patterns in the ocean and atmosphere. So the main one here that's been studied a lot is the Atlantic circulation in the North Atlantic here. And there's also possibly some in things like the El Nino, monsoons and jet streams as well, but they're a bit more uncertain. They're a bit more kind of controversial and haven't been fully studied. So over time, the estimates of the warming level required to trigger some of these climate tipping points have tended to fall. Back in 2008, it was thought that most of them would be in the 3 to 5 degrees range, so kind of, quite far away from where we were. But by the time of this plot from 2016, several of those thresholds have fallen. So you can see here that the West Antarctic ice sheet, Greenland ice sheet, Arctic summer sea ice, alpine glaciers, and coral reefs were all now potentially at risk within the Paris Agreement range of 1.5 to 2 degrees. And for example, West Antarctic ice sheet has fallen from 3 to 5 degrees to potentially being likely at only 1.5 degrees. That's a huge fall. And in the latest IPCC report, it stated that the risks posed by climate tipping points become moderate above 1 degrees, is high around 2 degrees, and very high beyond 2.5 degrees. There's also recent observations that suggest there could be destabilization in parts of West Antarctica and Greenland. And there's also some potential early warning signals of slowdown associated with potential slowdown in the Atlantic circulation as well. So there's some early warning signs that some of these might be getting unstable. There's also another risk as well. There's a possibility that because all these different tipping elements are in fact interconnected, that maybe tipping can spread through the system in something called a tipping cascade. So here on the left-hand side, we have some of these potential connections that have been suggested, and on the right-hand side, a particular subset of that, where the tipping of the Greenland ice sheet, for example, could make the AMOC, the Atlantic circulation, more likely to tip as well, and that has knock-on effects on the Amazon and the West Antarctic ice sheet. So if tipping one element makes another one more likely, there's a possibility it could spread. But this is a topic of active research, so it's still quite uncertain how this actually works out in practice. And in 2018, there was another paper that suggested this sort of behavior could help the Earth system drift from something like 2 degrees to 4 degrees over thousands of years because of this sort of tipping cascade. Although it's worth noting that was still a proposal, a hypothesis that hasn't been fully tested. So what are some of the research issues around climate tipping point science? Well, one thing to start out with is that the definition of climate tipping points often varies between papers, and it varies a lot in the media as well. Some of these headlines on the right-hand side here are all to do with, not actually to do with tipping points. The top one was just to do with the Paris Agreement warming level. The middle two are just to do with generic climate impacts like sea level rise that don't have a particular threshold that you get this self-sustaining change. So there's a bit of confusion out there in the literature and media. More specific to science, Earth system models have really improved over the last couple of decades, but there's still some processes that are missing that might help to resolve tipping. For example, I mentioned the Atlantic circulation. In the IPCC's latest models, that slowdown happens relatively gradually over time, but they also note that those models are probably biased to be overstable. We also know about tropical carbon sink, that the weakening of that we're observing now. The models don't really resolve that either. So there's some gaps between what we're seeing and what the models are able to see as well. We also don't have long enough observations to be sure of those trends. I mentioned the Atlantic circulation might be slowing. There's not long enough data to actually tell that apart from natural variability, and those early warning signals have a lot of uncertainty on them. So it's possible we could reach tipping points without actually being sure that we're approaching them. And lastly, this last big assessment I've been talking about was in 2008. There's been a huge amount of climate science advances since then, so we thought a reassessment would be timely. So that's what we did in this paper, published in Science in September. And in this paper, we compiled over 200 papers in scientific literature published since 2008, covering things like observations, paleo records, records of ancient climate change, and climate models. And from these, we were looking for evidence around all the proposed tipping element candidates that have been suggested. So from these papers, we synthesize estimates for the timescales, the thresholds, the impacts that are suggested or implied by those papers. And then using a definition of climate tipping points centering self-sustaining change beyond a warming threshold, we then categorize whether or not we think there's evidence for them being climate tipping points or not. And then from that, we separate those into either global core or regional impact climate tipping elements based on the scale of their tipping dynamics and also their impact, whether they affect the whole Earth system, whether they're more a regional thing that affects a lot of people. And this research was funded by the ERA project, which is funded itself by the European Research Council and also by the Earth Commission as well. And I did this work with colleagues from Stockholm University, Earth Commission, PIC, and the University of Exeter. So here's some results. This is just a map showing the 16 climate tipping elements we identified as having reasonable evidence for, although with varying levels of confidence that you can see in the full paper. We've gathered them into different warming levels, so the round red pins indicate ones that are potentially at risk below 2 degrees. The pink diamonds are 2 to 4 degrees, that's more kind of where we're headed. And greater than 4 degrees are the purple diamonds, the purple triangles, sorry, where hopefully we're not headed, but we still need to be aware of them. So you can see things here, Greenland ice sheet collapse, West Antarctic ice sheet collapse, abrupt boreal permafrost, Labrador Sea convection collapse, and Barents Sea ice. It's all being at risk sooner within the Paris Agreement range potentially. A bit higher, we have things like Amazon rainforest dieback I've mentioned, also the loss of alpine glaciers, mountain glaciers. We have Sahel greening, that's sort of kind of a reverse model. We get seeing more tree cover rather than less potentially. And we also have some extra ice sheets in the East Antarctica in the subglacial basins. And then a much higher warming, we have things like the AMOC, the full AMOC, things in the boreal forests, Arctic winter sea ice, and the collapse of more permafrost. So what are the potential impacts of some of these things? Obviously, the collapse of ice sheets could amplify sea level rise. Greenland and West Antarctica combined, something like 10 meters of sea level equivalent in them. But it's worth noting that if they were to collapse, it would happen over the course of thousands of years. But even so, it would still amplify the amount of sea level rise we might see even by 2100 by a substantial degree. Also, the loss of things like the Amazon, parts of the Amazon forest, or increased thawing of the permafrost through abrupt thaw, that could amplify global warming to some extent. Not more so than what we're already emitting, but it would certainly make it a lot harder to keep below 1.5 or 2 degrees. Obviously, there'll be huge biodiversity losses from losing things like coral reefs and the Amazon as well, and that affects the parallel ecological crisis as well as the climate crisis. And we have things to do with the regional weather patterns as well, and regional cooling from convection change in the North Atlantic and loss of sea ice in the Arctic as well. And that could really affect agriculture, particularly in places like North America and Europe, but also it could affect the tropical monsoons as well, so affecting agriculture there. Obviously, losing glaciers, loses fresh water supplies. That's a big issue in some particular regions, especially around high mountain Asia. And as we get into things like landscape disruption, so the boreal forest shifting and the permafrost falling underneath really disrupt those landscapes. And that affects the livelihoods of and lifeways of the people there, especially indigenous people. And more widespread, we have indigenous peoples in local communities in places like the Amazon being affected. And then coral reefs, something like 500 million people have their livelihoods connected to coral reefs through fisheries and coastal protection and things like that. So now just focusing in on the thresholds, the global warming thresholds that each of these climate tipping elements could tip at. So what this chart is showing, for each climate tipping element along the bottom here, the bold ones are the global core ones with the greatest global impact. For each of these, we have this burning embers bar. If we start at the bottom end of it, where the yellow starts, that's where we find our sort of minimum reasonable estimate from the literature, above which we are saying that tipping is possible, but not yet likely. The dotted black line, where it starts to go red, that's where our central estimate is. That's where the estimates from the literature are tending to cluster. So we're saying that's effectively our best estimate that we think tipping becomes likely from. And by the time we get to the dark red at the top, that's where we see our highest estimates from the literature. So we're saying tipping is probably very likely by the time we get there. This is not based on the quantitative probabilistic assessment. This is based on just pulling together those different estimates from different studies. So effectively, this is defining that as you go up these bars, tipping becomes more likely. And we can't be exactly certain when it might tip, but we're saying it's likely beyond that central estimate. To compare those for context, we have different warming levels of interest. This bottom grey line is current warming, about 1.2 degrees. The green lines here are the Paris Agreement range of 1.5 to 2 degrees. And this upper line, grey line here in band, that's where current policies are estimated to be taking us towards for 2100. That's about 2.6 degrees, give or take quite a bit of uncertainty because of uncertainty around climate feedbacks. And so based on this, we can say that at the current warming level, 5 climate tipping points are possible in that bottom grey line is starting to nudge into the bottom end of those bars. They're possible, but not yet likely. And these are the Greenland ice sheet, the West Antarctic ice sheet, low latitude coral reefs, boreal abrupt permafrost fall, and the Labrador Sea convection collapse. By the time we get to 1.5 degrees, we actually nudge into the likely range of 4 of these climate tipping points. They reach their central best estimates, and 6 are possible. Staying below 2 degrees is still kind of within the Paris Agreement range. 6 become likely, and 4 are possible. And by the time we get to the 2.6 degrees, that policies are taking us towards by 2100, 7 are likely and 6 are possible. We can't be certain exactly how many are likely or possible at each level, but there's definitely an increasing likelihood the further goes up. So yeah, that's that first point there. What I've added here is the side plots are showing how that relates to future emission scenarios. So again, we've got the IPCC scenarios, the blue and the green ones are the low emission Paris compliant scenarios. The orange and red are if we go backwards and start to emit more carbon than now. And we're roughly on the middle yellow halfway here. And then in the bottom right-hand panel C, all we're doing here is just counting off how many of these thresholds we're passing on each of these different future scenarios. And you can see that even with all the blue and green low emission scenarios, some of these thresholds are passed in the coming decades. But sticking to those low emission scenarios compared to the red and orange ones up here, we can still avoid most but not all of these thresholds by sticking to low emission pathways. It's also worth noting that a couple of these lower 1.5 degree thresholds for the ice sheets, they have a bit of they take a bit of time to actually start tipping, so we might be able to overshoot them for a few decades and not actually tip them. So if we get back below 1.5 degrees by the end of the century, it might be possible that the Greenland ice sheet and the West Antarctic ice sheet won't tip. So there's a bit of uncertainty there, but definitely it shows the risks involved. So finally, just coming to the implications, clearly this research suggests that the 1.5 degrees Paris Agreement ambitious aim is a good one, because that would reduce the likelihood of passing multiple climate tipping points, as well as reducing all the other climate impacts that the IPCC have been talking about for a long time. It doesn't eliminate the possibility of climate tipping points, but it does reduce it. It gives us our best shot. In order to reach this, emissions have to fall by around about half by 2030 and reach around net zero by 2050. And this plot on the right-hand side here is just giving an indication of where we need to be versus where we are. We're on this upper blue pathway here, and we should be on this lower green pathway. And even the more ambitious promises that have been made, that are those middle lines, that policies don't yet follow, even those aren't enough for 1.5 degrees. Based on our research as well, even if we were to keep to 1.5, we can't rule out climate tipping points, so that needs to be considered in adaptation planning as well. I mentioned there's a parallel ecological crisis, so there's a possibility that some of the natural climate solutions being suggested might help protect us, particularly some of those biosphere-based tipping elements, by helping to support ecological regeneration, as well as trying to draw down carbon into the biosphere as well. But it should really be noted that carbon removal potential of natural climate solutions is limited. It's definitely not a silver bullet, and beyond 1.5 and 2 degrees, they're gradually more and more threatened. They might not keep that carbon in them. So there really is no alternative to emission cuts to try and reduce the risk of reaching climate tipping points. And finally, this is the point that Lloyd will be talking more on. We can see that the incremental change, incremental promises and policies that are in place aren't enough to keep that 1.5 degree pathway. So in order to get to sort of much more transformative change required to get towards that green line, we might need to think about whether there's positive societal tipping points that could accelerate decarbonisation and other sustainable transformations. And that's something that Lloyd will be talking about. And it's also something that the project I'm involved with now at Exeter, there's this State of Tipping Points report where for COP28, this year's UN climate talks, we'll be doing a review of some of the updated review of Earth system tipping points, the negative ones I'm focusing on here, also some of the socio-ecological impacts of those, and finally looking at the positive tipping points as well in more detail. So yeah, just to wrap up, I've talked about climate tipping points, how they involve change becoming self-sustaining beyond a certain warming level, locking in big impacts. And I've talked about how by the time we get to 1.5 degrees, several of them are potentially becoming likely. And this provides really strong scientific support for why the Paris Agreement aim of 1.5 degrees is such an important level to try and keep to, because it reduces the likelihood of passing tipping points. And this requires immediate emission reductions as soon as we can, alongside adaptation investment and ecological regeneration as well. And that's it. Thank you.
Thank you so much, David, for that fascinating in the Q&A box, and we will address them during the discussion session with the next speaker. It was really interesting. Rolling off the end of the seesaw is certainly going to haunt my dreams. But hopefully we can turn now to David, to Lloyd. As you said, David, there's this huge gap between where we are and where we need to be. And it will be great to hear from Lloyd a little more about how the social trajectories we're currently on might be subject to tipping points for transformative change too. So Lloyd Pinnell joins us from Systemiq, where he is an associate at this leading systems change consultancy, working to deliver on the objectives of the UN Sustainable Development Goals and the Paris Climate Agreement. Lloyd works in the energy and sustainable finance platforms, advising investors, companies and governments on strategies to reach net zero emissions and to unlock opportunities from the transition. Lloyd recently co-authored The Breakthrough Effect, a report exploring the potential to trigger tipping points from the deployment of zero carbon solutions to decarbonise the highest emission sectors in the economy. This follows on from the Paris Effect report series, which examined how global climate agreements are fundamentally reshaping the global economy. Lloyd, the floor is yours.
Thank you very much, Ruth. Thank you, David, for a really excellent and interesting presentation. I'm just sharing my screen now.
That looks good, actually, Lloyd.
That's working, is it? I'll just go full screen.
Perfect.
That's all right. Okay, thanks. Oh, whoops. Thank you. So yeah, as Ruth mentioned, Lloyd from Systemiq, and we recently published this report called The Breakthrough Effect that came out last week. And I will sort of focus on the learnings and the key summary findings from this report, in particular what I'm going to say today. David spoke to us about negative climate tipping points, which are obviously terrifying, and we're clearly getting dangerously close to them, as David showed us. So we need to accelerate things as much as possible. Tipping points also exist in socioeconomic terms. They are present throughout our economy. I'm going to talk you through today sort of where they might exist and what we could do to bring them forward, and explain why we think they might offer a lifeline, or at least something to focus on to accelerate change if we want to stand any chance of meeting the goals of the Paris Agreement, which every year look increasingly more difficult. So what is a tipping point? Let me start here. I'm sure most people will have heard of it, either applied to climate or applied to socioeconomic phenomenon. This obviously was popularized a few years ago in a famous book by Malcolm Gladwell. And there has been a lot of research on this in recent years, especially. So we define socioeconomic tipping points as when new solutions, and these can be either technologies or practices, advance to levels where they start to rapidly outcompete and replace existing solutions. Why are they important? So once you cross a tipping point, what happens is your new solution, your new technology, or your new way of doing things will grow exponentially and force out of the market the old solution that it's replacing. And this, once you hit a tipping point, happens quicker than anyone could have predicted. So as I said, triggering tipping points could offer an opportunity to rapidly increase the deployment of zero emission solutions and cut global emissions over the coming years. So there are actually many examples in history of new inventions hitting tipping points. What I show on the right here in these two charts are a sample from history of new innovations that have reached full adoption in a relatively short period of time. On the top one, you see those from infrastructure and energy systems across different examples, and on the bottom chart, you see those from manufactured goods. They're all normalized to show essentially lines going from 0% of adoptions when these things first enter the market to when they reach almost full adoption. So in the case of the US, for example, every household having a refrigerator or a microwave. And I think some of these give us some cause for hope. When you see timescales of 2 to 3 decades for reaching full adoption for new solutions, they give us cause for hope for scaling zero carbon emission solutions in time to reach net zero. So to take a concrete example, microwaves went from in 1980 from just entering the market to by 2010 and 30 years, being present in almost every household. And you could imagine something similar could happen for, say, heat pumps or other solutions. It's also true for large infrastructure projects. So shipping port infrastructure in the US for sort of heavy goods shipping was developed over largely a 20-year period. Similarly, in France, nuclear power stations were built over 10, 15-year period extremely quickly. So these things are possible once they hit their tipping points. How do tipping points work? Well, we've come up with a framework based on literature review of various sources and input from different experts in this field, looking at some of the conditions that would be required for tipping points to take hold. And we broadly categorized the enabling conditions into 3 different categories. And these are things that need to be in place, essentially, for a tipping point to take hold for this new solution, this new technology, or this new practice. The first is affordability. So here, what we're saying is that you need the solution to reach or be near to cost parity relative to the incumbent technology, with or without a type of policy intervention to bridge that cost differential. So this is often sometimes referred to as green premium. And the policy intervention could take the form of a tax, a subsidy, a market shaping regulation. It could also just be a carbon price, as is often depicted. And what you see here is a sort of graphical representation of what that could look like. Essentially a policy bridging the green premium to bring forward the date of the cost parity between two solutions. One, a representative high emissions fossil-based solution, and another a zero emissions renewable-based or other solution. But that's not all you need. You need also two other conditions broadly to hold. One is attractiveness. So you need an improved performance from your new solution on non-cost reasons. So this could be across quality, reliability, convenience, or something else. A good example of this is household central heating, which, as we saw in the previous slides, took over full adoption in the US market in a matter of 2 or 3 decades. And that not only became cheaper than the existing solution, largely of using wood for heating homes, but it also offered a much safer and easier option for heating your home than that solution at the time. And lastly, it needs to be widely accessible. So the supporting infrastructure for large-scale adoption needs to be in place. A good example here is the rapid rise in electric vehicles in Norway. That was actually preceded by a government rollout for increasing access to charging points strategically across the country, which actually did play a very important role in supporting the tipping point that we saw in Norway, where they have in fact gone from about 1% of the market 10 years ago to over 90% of new cars sold last year being electric in Norway. The other thing that's you need for tipping points to exist are strong reinforcing feedback loops. Now, reinforcing feedback loops, there are many different examples of these. I've listed a couple here, and you can refer to the report for a full list. These are things like learning by doing effects that improve performance as you scale the technology, economies of scale that reduce costs as you expand the production of the technology, or the spread of new social norms that radically transform the acceptability of the new technology or practice. Now, why do you need these strong reinforcing feedback loops? Because these allow for self-accelerating progress, where the greater the deployment of the solution brings improvements either in cost or performance or accessibility, which then creates an incentive for even more deployment. And that's what gives you this exponential shape of the curve. So that's when you hit the part of the S-curve where you're growing exponentially, is because the more you deploy that solution, the more attractive it is to deploy that solution. So the more you do it, and you get that rapid tipping point effect. There's a graphical representation here of what it looks like in terms of adoption. So first, the flow is affected. This could be, for example, the percentage of new sales of cars, and then it translates later on, given the stock turnover period, to a percentage of the total market share. So this would be how many cars are electric in the total fleet. And then we argue there are different drivers that make these conditions possible. So buyer preferences, market development, so this is what businesses are doing and investing in, and policy support, so how governments are intervening in markets. These are the three things that will essentially make these conditions happen so that tipping points can take off. The good news is these 4 charts essentially. So these show learning curves for 4 different technologies: solar and wind power, batteries, in this case lithium-ion batteries, and electrolyzers, which are the technology required to produce green hydrogen. These we refer to collectively as the 4 horsemen of the energy transition. They are kind of the core workhorses that will deliver the largest part of emissions reduction in the energy system. And the good news is that they all have potential to have massive cost reductions over time and hit their tipping points. Why? Because they have these self-reinforcing feedback effects, especially in this case in the form of learning by doing effects. So what does this mean? This means essentially the more you build solar, the more you develop wind turbines, the more we learn to make them more and more cheaply. And we've seen this. So for example, solar over the last 10 years only, the average cost, measured in levelized costs of energy, has fallen by 85% in the last 10 years, whilst we've increased our production capacity of solar panels by 20 times. Similarly, for lithium-ion batteries, we have increased the production capacity by 100 times. We've now got 150 gigafactories around the world producing lithium-ion batteries. And over that time, the average cost of the battery pack has come down by 90%. But that's just the start. So what we show here in these charts, and why we split them into two, is we show the historical element. So we say this is the cost reduction that's happened over the last 10 years with the increase in scale that we have seen so far. And then we show in the future, in a projected net zero scenario, so this is what we would need in terms of deployment of those solutions to reach a net zero energy system by 2050, what that would imply in terms of further cost reductions, assuming that the learning rate stays constant. So assuming we keep learning to make solar panels cheaper with every unit of output increase as we do today. And you see that we can expect actually much more drastic cost reductions in those technologies. The core reason for this is because these are modular, replicable technologies. So they're small in size, they're distributed, they're easy to replicate, and they're much less complex to manufacture than big projects, which means the learning rate is very high because we're constantly repeating, finding new ways to innovate and reduce waiting times or input costs, etc. There's very strong knowledge diffusion as well because it's a global industry. And so any new information travels to other parts of the world very quickly. So we've actually consistently underestimated the cost reductions we would see from these technologies. 10 years ago, the average expected annual reduction in cost for solar panels was 2.6%, whereas over that 10-year period for which it was predicted, the actual annual cost reduction was 15%. So we're consistently massively underestimating how much the cost of these technologies is going to come down. And we argue that under a net zero scenario, we could still be doing that, and there could still much cheaper technologies. So what we do, we then build on that in the report to identify tipping points by sector. And what I've shown here on the right-hand side is an example of the output we have where we identify tipping points by sector. So what we do is for the 11 highest emission sectors of the economy, we identify one key zero emission solution that we think is going to provide the bulk of the supply side decarbonisation in a transition to net zero. So for example, in the shipping sector, we focus on green fuels. Obviously, in every sector, many different things need to happen to get to net zero. There's going to need to be a mix of energy efficiency, resource efficiency, behavior change, etc. But typically, in an end state in net zero, there is one major zero carbon solution that dominates. In the case of shipping, green ammonia, we believe, is going to make up 80% of energy demand in a net zero scenario by 2050. So we focus on those, and we try and find which conditions are required across accessibility, attractiveness, and affordability to hit those tipping points. It's a review of the evidence we have to date on those. Another piece of good news, we think we have very much already hit a tipping point in the power sector. Solar and wind power are now, as I said, the cheapest forms of new electricity generation almost everywhere in the world. And last year, 85% of all installed power generation capacity globally was from a form of renewable electricity. 3/4 of all power installed was solar and wind last year. That's what a tipping point looks like. We think we're very close to one on electric vehicles. However, looking across the other parts of the economy, our confidence in the potential to see these tipping points and SCEV adoption for new zero carbon solutions differs, and it differs based on the existence and the strength of these reinforcing feedback loops I talked about. So there are some areas in which we have high confidence that tipping points are possible. This includes the passenger vehicle market for battery electric vehicles. It also includes heavy duty road transport with battery electric trucks. And in those sectors, battery cost declines from scale effects are very well evident. We have high confidence in those. In others, we have more of a medium level of confidence that tipping points could be hit. So alternative proteins, we believe it's likely that there could be social diffusion dynamics around diet, where the more you scale and the more people consume alternative proteins, the more it becomes accepted and it becomes a norm in society and so on. But that's not still very well understood, and it's going to very much differ by geography in local regions, depending on the culture. And there are others where we have more of a low confidence at present that tipping points could exist. This includes actually, funnily enough, heat pumps, because the cost and attractiveness advantage of heat pumps over gas boilers is very hard to achieve and maintain without continued policy support, without policy support always bringing down the upfront cost of a heat pump versus a gas boiler, which means it's unlikely that we see exponential growth, but we could still see very strong positive linear growth in a kind of best case scenario if policy pushes the market in that direction. So how do we trigger tipping points? This is our kind of summary chart that rolls up all the information we've gathered across sectors on these topics. And what we try and argue is that we want to create the enabling conditions for these zero emission solutions to start outcompeting the incumbents on these three different dimensions. So on affordability, for example, even with a regulatory push to create the scale for cost declines, some solutions, mainly the ones that are linked to hydrogen, green hydrogen as an end use for decarbonisation, will likely require a carbon price to bridge the remaining green premium. So we think in the steel and shipping sector, even if we can get hydrogen down to $1.50 per kilogram of hydrogen, we'll still probably need a carbon price or an equivalent form of tax or subsidy mechanism to bridge the remaining green premium with fossil fuels of around $100 per tonne. That's actually not very high, and that's actually something that politically is feasible in a lot of places around the world, and we're not that far away from that today. So Europe's carbon price is currently in the 90s, 90 euros per tonne. So we think that's tough, but it's doable, and we could trigger tipping points in quite a few sectors because of that. And attractiveness is very important. There's accessibility. There we talk a lot about how many public charging sites we think we would need to trigger a tipping point for electric trucks, for example. So obviously lots of information there, I can't go through it all, but what it leads us to is this sort of overview by sector of different gaps essentially in the enabling conditions for tipping points to take hold. Now that leaves us with two options. You could either focus on the areas where the biggest shifts are still needed to unlock tipping points, the reds, as you can see here. For example, in the power sector, we need to do a lot more work on transmission distribution to connect generation of renewable electricity with the places where we're going to need it, and we're severely behind on planning and permitting. Or the second option would be to focus on the early wins. So can we push sectors that are near tipping points but not quite there? Can we push them over the edge onto a tipping point so that we then get that exponential growth and decarbonize that sector more quickly? We actually argue that option 2 might make more sense. Why? Because of things we call tipping cascades of tipping points across sectors. So we have here again lots of information here, I won't go through it all, but broadly what we're arguing is that high emitting sectors of the economy don't exist in isolation, they're deeply interconnected, and zero emission solutions such as the 4 we mentioned earlier can influence transitions across multiple sectors simultaneously. So that if you trigger a tipping point in one sector, it's actually going to influence the likelihood of triggering tipping points in other sectors, which means you can focus on these low-hanging fruit, these sectors of the economy that are closest to tipping points, and try and use those as a leverage point to then increase the likelihood of tipping points in other sectors. And we put out 3 from the systems mapping exercise you see here. The first is electric vehicles in light-duty road. The second is green ammonia use for fertilizer production. And the third is alternative proteins in the agriculture, food and agriculture space. And there we suggest using mandates and public procurement in the case of alternative proteins to increase the production of those technologies quickly and create the enabling conditions required for those tipping points to take place. Why is that? Well, I'm running a little bit out of time, but I will talk you very quickly through the rationale for those different super leverage points. Why I focus on mandates for battery electric vehicles. This was actually one of the key recommendations from the UK government's review of net zero recently. Well, the reason is because we think by forcing that supply of batteries, you're going to drive down the costs for solar and wind, which is also going to make it cheaper to store energy in the power system to complement solar and wind. So we have more renewable energy throughout the day when the wind is blowing, the sun isn't shining, at a cheaper cost, and that's going to lower operating costs for other solutions across the system that rely on cheap renewable power, heat pumps, electrolyzers. Similarly, mandates for green ammonia. We think if you provide that initial scale production of green hydrogen for use in the fertilizer sector, which is the one that's currently the most suited for a series of reasons listed here, to provide that initial scale, well, then you're going to drastically reduce the cost of green hydrogen as you push down that cost curve, and that's going to make it more feasible for us then use that green hydrogen in other sectors, steel to produce green steel, in aviation, in shipping to produce green fuels. Yeah, and basically by providing that initial scale, you're going to drive the cost down, and that's going to allow decarbonisation, the frontier, to be pushed so that other sectors can also be decarbonised. And lastly, on plant-based proteins, so we think product procurement is a good source to provide the initial scale to drive down costs and critically also improve the taste, texture, and nutrition of those alternative proteins, which will then decrease the demand for meat, reduce pressure on land, and thereby lower the incentive for deforestation. So I see Ruth popping up, which means I might be running out of time. So I'm just going to skip over this and invite you to check the report if you're interested in more details on it. And I'm just going to land on the summary very quickly to preempt a few questions I imagine will have come up in the chat, which is to say, what did we do in the report, and what did we not do, and where do we go from here? So the first is, what did we do in the report? Well, as I've tried to argue today, we think there are many positive socioeconomic tipping points across the economy for these zero emission solutions. We think they offer us a real chance of accelerating change if we want to stand, any chance of reaching the goals of the Paris Agreement and limiting global temperature rises to below 1.5 degrees. We focus on analysing the enabling conditions that would make those tipping points possible. And we highlight a couple of super leverage points in the system where we think one tipping point might trigger others in other sectors. So what? Well, we think governments should start potentially prioritising investments that can create those conditions and unlock those tipping points, especially in the super leverage sections. We also think philanthropists, private investors with a climate focus should start building this framework into their thinking and target investments to the areas that could have the highest return in terms of decarbonisation, so the areas where tipping points are possible. What did we not do in this report? This is very important. We just focus on these scaling effects, right? We didn't cover other things that are equally important in the transition to net zero. That is stuff around measures to improve energy and resource efficiency to lower overall demand, the role of behavioural change, and interestingly, the existence of tipping points within behavioural change, and of course, supply side measures focused on reducing the supply of fossil fuels and preventing further production of fossil fuels. So what's next? Well, as David said, there's a really interesting research project going on at the University of Exeter in collaboration with other groups, looking more into these questions. A lot of the things we found was that areas we explored were still lacking in evidence and supporting data analysis, so a lot more needs to be done researching this topic. We hope this framework can be extended further to be applied more widely and to cover some of the technologies and system interactions we didn't map. And lastly, we would like, in a perfect world, people to start integrating this way of thinking into things like carbon abatement curves, which determine a lot of investment today, don't necessarily take into account those reinforcing feedback loops that we've identified across the system, as it could really have an influence on the return on investment in carbon terms for how we prioritize resources today. That's it. I think I'll leave it there and pass back over.
Thank you, Lloyd, for that excellent presentation. That was really interesting and great to hear those perspectives on the industrial challenges and also the sort of market-based potential solutions for social tipping points. I think that we're still taking questions, and I can see there's a really lively set of questions here, so I might have to knock on the head my moderator's privilege of asking the first question and jump in with your questions. So first of all, I'm looking at the upvotes that questions have, and Laura and a lot of people have sort of questioned thinking about socioeconomic tipping points from this market-based perspective alone. I know that Lloyd, towards the end of your talk, you mentioned the behavioural elements not being covered, and I'd also like to point people back to the previous session that I mentioned in my introduction, tipping points for positive social change, which was also part of this series, which takes a more behavioural perspective. But interesting to see that is important to people, that we're taking this kind of broader view. So the next most upvoted question from Emily Robinson, so this is to David, I think. Does the research model other net zero pathways? This is a very techno-optimist analysis, but new research has indicated that policies make cities more walkable and public transport more effective and accessible, lower demand for finite materials by between 18 to 66%, which would help counter other problems such as geopolitical tensions and concerns with supply chain bottlenecks. Research also indicates that it would offer quicker decarbonisation pathways. Would someone like to jump in and answer the question?
Yeah, I can take that one. I think it's more directed at the our side of things. I couldn't agree more, and that's why I noticed just at the end that we did focus specifically on this potential effect of scaling zero emission solutions. But we do that, and we don't really look in much detail at energy and resource efficiency and how you know that interacts. But what I would say is that's step one. So you know we've got to do everything we can to reduce demand for energy and resources, and that example is a wonderful case study of making cities more walkable. I don't think that will provide the entire solution. We'll need both. In a perfect world, where you would get as much as you can out of the reduction in demand and the improvements in efficiency, but you're still going to need to scale these solutions. I don't imagine a world in 30 years where cars won't exist. So we still need, you know, beyond everything we can get on the efficiency side to scale the replacements that are clean.
Thank you, Lloyd. The next question that we have is around why speakers are not actively recommending direct action and upping tactics of protesting. There's some interesting research out there around the sort of social thresholds at which protesting has, in historic examples, elicited social change, such as around the civil rights movement in the US. Which hopefully we can direct you to afterwards. But I was also interested in both talks in thinking about communicating threats of this magnitude. So I'd be interested in both speakers' views on your thoughts about how best to close the gap between scientists and indeed concerned members of the public on and leaders on the magnitude and urgency of climate action that is necessary. So that's both in terms of the science for David and in terms of the role of social change and the need for government support for industry such as subsidisation from Lloyd's perspective.
Yeah, I can jump in first. So yeah, I think this is a really interesting question and good point. Obviously my presentation was more to do with the science, and I'm really interested in how communication around this sort of science, climate science and climate tipping points in particular, can happen. Back in September, there was we had a conference in the University of Exeter to do with tipping points, and I was co-convening a breakout session specifically on climate science communication around tipping points and also social movements, because there is a sort of strong connection between how we communicate science and how that triggers societal action. And I do think it's really important that we need to be engaging with social movements. I think social movements are a really big source of potential societal tipping points. But I think it's the sort of thing that is needed, tipping points in social movements that can help keep the pressure up and put the pressure on politicians to help these sort of more technical tipping points be pushed over as well. So I do think social movements are really important to consider there. And I do think scientists can do a lot by engaging with social movements, sharing their science directly with people, and not just always aiming towards policymakers, but also talking directly to activists and the public in quite a sort of open, conversational way to get this sort of information out there. So yeah, I definitely think social movements are an important part of trying to accelerate change in society.
Thank you, David. Lloyd, would you like to come in too?
Yeah, sure. I mean, I would say, I would echo that and say, you know, of course, social movements are crucially important. I would say, I think you need to couple it also with some of the messages we have in our report, which is that a low carbon net zero future is not one in which we're worse off. It's one in which actually things are much better. We have cheaper energy. We have more mobility. We can support growth in low-income communities through some of these solutions. And I think it's only when you combine those two messages that we need to act quickly, but also the solutions we have offer a better alternative, that we're actually going to get, you know, the full spectrum of engagement politically that we need for rapid sudden change. And I think you're actually starting to see that. I think people are coming round to that view, and that some of the policies that we've seen come in through the last few years, whether in Europe or the US with the Inflation Reduction Act, are really important steps in the right direction. And I think they're going to have their own sort of tipping points in a way where we'll realize how beneficial to society and to the economy those measures have been, and it will lead to even more action. But they couldn't have happened without the social movements, and they should continue to up the speed of change, because we're still far behind.
Thank you, Lloyd. Okay, next question from Hannah. I can't help but think that the trade-offs associated with some of these solutions. In your opinion, Lloyd, is there enough of an understanding of the trade-offs as well as the benefits of some of the technological changes? For example, what about the environmental impacts of mining or the competition for land use? For example, agriculture versus solar versus wind.
Yeah, absolutely. It's a good point. I mean, I think I'll take the two examples one by one if I could, because they are, I think, really good examples actually. So on mining, obviously the transition to electric vehicles and to all the other forms of low carbon solutions, the inputs to other low carbon solutions we need, like electrolyzers, we will need a lot more critical minerals, and we'll need to mine them often from new mines. But if you compare that to the equivalent volumes of mining from fossil fuels that we need today, I mean, it's dwarfs, it's minimal. And that's not to say there's not issues with it. There are lots of risks, ecological, social, around where those mines will come online. But I think we have to recognize also that the transition to these low carbon solutions will actually involve much less overall volumes of mining than we would have in a world with fossil fuels. Which is not to say we shouldn't minimize as much as we could through the resource and efficiency measures as a first step, but we will unfortunately need to bring those supplies online and develop those solutions. And the second example, which I've now forgotten, was, I believe, land use, right? Of course, land use. Yeah. Again, in terms of land use, solar and wind does take up a fair amount of land, but if you put it into its rightful context, the amount of land you would need for a fully decarbonized energy system, it's actually quite minimal, and you can put it in the right places, and you can crucially combine it with existing uses of land. You can put solar farms on existing farms and still produce the same amount of output. You can put wind offshore. You can put solar panels on top of houses. There are lots of ways around this, and I really don't think the land availability constraint is a major one. We've done a lot of analysis on this in the Energy Transition Commission with Systemiq, and if we do it right, I think it won't hold back the transition.
Thank you, Lloyd. Unless you want to come in, David, shall I move to the next question? Okay. So from Felix Bittner, is the current economic climate, as well as rising inequality, making it less likely for these tipping points to happen enough? Public spending for consumers to afford these technologies? Do we need more progressive taxes and redistribution to be able to support these technologies adequately?
Was that one for me again?
I think it is. Sorry,
Yes.
you're getting hammered
Sorry.
here, Lloyd.
No worries. I just lost you in the middle of the question. So I think I got it, which was to put it back. Are we going to need it? Well, I think there's two parts to the question, right? The first is the current economic climate likely to delay the triggering of these tipping points? And the second one is, do we need more progressive taxation? I think I'll answer the first. I mean, the second one I have a personal view on, but it's not really the topic of our report. I think obviously we'll need a lot of public spending. Where that money comes from is kind of a second matter for debate. Is the current economic climate likely to delay the transition? That is very much a possibility, yes. I mean, we think there's a few elements to it. One, for example, is that at the moment with inflation and supply chain bottlenecks, we have extremely high lithium prices, for example, that is likely to potentially delay by a few years the cost parity between electric vehicles and internal combustion engine cars. That's one example. There could be more. It's hard to know right now where they will exactly land and how long it will last for. A lot of the spending we need to do on energy projects in particular are very high capex, so you need big loans, and with high interest rate environments they're harder to do. However, the good news is that a lot of the spending we need to do on the energy transition is disinflationary. Because we have such cheap solar and wind today, they can actually have an impact on reducing inflation, and you're seeing that in Europe at least, that renewables are being used as a tool to reduce inflation in some cases. It will take a long time. The current planning and permitting timelines mean that they take a long time to come online, but they are a useful weapon in our arsenal against inflation. I had another thing to say that's escapes me now, so I'll come back to it.
Okay, thanks. David, I've pulled together a couple of different questions for you around the parameters of your work to define tipping points. Does the work take into account things like logging in the Amazon rainforest and other human activities that may exacerbate dieback? And to what extent does this analysis account for extreme events triggering transitions? Also, further to those questions, the research on climate tipping elements are a key information source to assess the long-term risks associated with different global mitigation policies. But which tipping elements, other than those relevant to sea level rise, are close and relevant enough that they should already be considered in planning climate adaptation policies in Europe? Sorry, that's a lot to handle. Come back to me if you need to repeat anything.
So the first one was to do with the Amazon. So in this paper, we decided to focus specifically on climate change as a driver for these tipping points. So when we talk about a climate tipping point, it's part of the Earth system, the climate system in particular, that can tip as a result of climate change. Deforestation can also help trigger or trigger on its own Amazon dieback. And then there are separate estimates for this. So we use the climate-only estimate of a threshold somewhere around 3.5 degrees of warming could trigger enough drying out to cause Amazon dieback. And then the equivalent for deforestation is something like 40% deforestation could trigger wider dieback as well. The trouble is there aren't very many studies that combine the two, because obviously both of them are going on at the same time. We have deforestation currently reaching around about 18% across the whole basin, and we have warming already at 1.2 degrees, which is causing increasing severity of droughts in the Amazon. How the two interact with each other, we don't know how low that makes the combined threshold. Carlos Nobre, a Brazilian researcher, has said that anything beyond 20% is entering the risk zone for deforestation. And we just don't know what the combined threshold would be for warming if we're also considering deforestation. So that makes actually Amazon a little bit more at risk than perhaps would be first apparent from our climate-only summary in the paper. The second one was to do with extreme events. So that was in the paper, we're looking at sort of the combined effect of different climate impacts happening at the different global warming levels. So that's somewhat implicitly including extreme events, but extreme events are somewhat underrepresented in climate models because climate models tend to inevitably they're a bit granular, low resolution. They can't cover all of the potential really short-term and small-scale extreme events that can happen in reality. So I'd say that extreme events in there, they're an important part of climate tipping points, but current research is probably not quite up to scratch to fully include them, and that's an important thing to look at in future. I've been talking to researchers to do with coral reefs and mangroves in particular, who are interested in how compound extreme events could push them beyond tipping points rather than just warming directly itself. And that last point was to do with the global effects of various climate tipping points and adaptation planning. So yeah, a lot of those climate the impacts of climate tipping points will be somewhat global. For example, the sea level rise already mentioned, but also the amplification of global warming beyond what we might expect otherwise, which I was talking about being sort of, for example, permafrost could amplify warming by something like 10% or more on over the course of a couple of centuries. That's one thing worth bearing in mind. But in terms of more kind of regional scale things to be aware of, the Labrador Sea convection collapse is an interesting one because that can happen quite soon, maybe at 1.8 degrees or so, and that would have quite significant impacts for Europe, causing kind of a smaller scale version of AMOC, the Atlantic Circulation Collapse, causing regional cooling. It disrupts the jet stream, it changes extreme weather patterns. That could really affect agriculture both in Europe and North America, but that also affects the monsoons too. So I think that's probably a good case study that we need a lot more work on to actually give specific recommendations to countries that could be affected by something like Labrador Sea convection collapse, being like, this is what your country can expect if this happens. It can happen sooner than we thought. So you probably want to start including that. And also things at 1.5 include like coral reefs. So countries with a lot of coral reefs need to be aware of the fact that they're likely to experience increasing levels of die-off. So they need to be those communities need to have support in trying to deal with that, hopefully using also some kind of ecological regeneration to try and protect those reefs, as well as prepare for the fact that their livelihoods might not be able to rely on coral reefs as much. And this is where loss and damage comes in as well.
Thank you. So we've got a comment that it would be great to hear more perspectives from the Global South on the topic of social tipping points. Interested in Lloyd's perspective on this from a sort of analysis of different industries and looking at perhaps a kind of critical consideration around different changes to the mining materials that are needed in the transition to a low carbon economy. Is this something you want to cover, or David, if you have any comments on the perspectives, social tipping points, that'd be great.
You go first, Lloyd.
Yeah. Sorry, Ruth, I actually just lost you temporarily, so I didn't quite get the question. And
sorry, I think my internet cut out briefly. The question was perspectives from the Global South on the topic of social tippings. I think from either of the perspectives of your talk, it'd be good to hear what you have, your thoughts on that.
General perspectives from the Global South on the tipping points.
People saying that it would be good to hear them, and I'd be interested to hear whether you've managed to include that in research at all, or any future plans to.
Yeah, I mean, it's definitely something we'd like to do more of. I obviously can't speak to perspectives from the Global South. What I can say is I think, a lot of these tipping points, they do offer positive growth stories for a lot of regions in the Global South. When you talk about the future of the green hydrogen market, there are really exciting plans at the moment in Southern Africa, in Brazil, for developing those markets of the future, and we think that there's real opportunity there to use those as drivers of growth and development in a lot of regions around the world, if it's done right. It can obviously go either way depending on how those projects unfold, but the potential is definitely there. What's really exciting, I think, about some of these technologies we're talking about, like solar and wind, is that they're distributed in nature, right? So that you can have solar homes in sub-Saharan Africa. So it completely disrupts, the more oligopolistic nature of the fossil fuel industry. And it distributes power and it distributes energy provision, and the revenues from those across the community more widely. And hopefully, that will have quite a big effect, we think, on both growth and also income redistribution.
Yeah, I think it's really important to have Global South perspectives in here. I think in general as well, societal tipping points are probably going to be looking, there'll be some commonalities with so societal tipping points in the global north, but in the global south, they might look relatively, there might be sort of different aspects that might be more relevant. So I think in terms especially of adaptation, I think there's a lot of adaptation that will be useful to be pursuing in the global south, particularly from a socio-ecological perspective. For example, in the Amazon rainforest, trying to reduce the pressures on the Amazon to reduce the chances of dieback, but also make those areas more resilient to further climate change and further drought. There can be things people proposing being a sustainable bioeconomies in the recent science panel for the Amazon talk, where effectively local communities and indigenous peoples in those regions can be regenerating the forest, but doing so in a way where they can earn sustainable livelihoods from those areas. And there could be societal tipping points associated with that that help both regenerate the forest and give it more resilience, as well as providing people's livelihoods. So I think that sort of thing is an important aspect that would be particularly relevant in parts of the global south that are directly facing some of the impacts of the climate tipping points I was talking about.
Thank you, David. So next question is from Tim. I've read a lot about analysis of critical slowing down, where early warning signs of approaching climate tipping points can be detected in either present or paleoclimatic data. Has any such analysis ever been done with social or socio-economic tipping points?
Yeah, so this is something that some of my colleagues actually at Exeter are working on. I won't go into too many details so that I'm not spoiling their research when it comes out. But yes, there are plans afoot to look more directly at socioeconomic data and try and look for, well, we call them early warning signals normally when applied to the more negative tipping points we're talking about in climate or in ecosystems, but they're sort of thinking more in terms of them being good things, so early warning signs of good shifts approaching potentially, and also of potential negative societal tipping points as well. So that is definitely something that is going on now. It's just not quite as advanced as some of the physical science early warning signals.
Yeah, I would just say the same thing that you know, David's colleagues Tim and Jesse at the Tim Lenton, this is at the University of Exeter, are actively researching that topic, and there's lots of very promising avenues, I think, for that work. One quite interesting example is in the US, the coal sector had a sort of financial collapse before output collapsed, and you could see it retrospectively as an early warning signal, where the value of shares in US coal companies plunged actually far before output did. It then preceded a period in which US coal production and shares then dropped massively over a 5-year period. And so those are some of the avenues that are being explored, and I think more others too.
Thank you. My colleague Bernice Lee's comment as we were sort of commiserating and discussing the outcomes of COP27 was that not many people would be coming away from that conference and thinking now's the time to invest heavily in fossil fuels. But interesting to see whether that has played out. Okay, so next question is from Sophie Hebden. Is there research into the interactions between climate or ecological tipping points and human systems yet? For example, poverty thresholds pushing people into wood harvesting and decimation of scrubland biomass or causing desertification?
Yeah, so this is there's a lot of research in socio-ecological systems looking at how various different drivers, including climate change, but other drivers as well, affect these systems when you look at ecosystems not just as separate biophysical systems, but incorporating humans, because that is actually the situation we live in the world. And you get all these sort of interesting non-linear dynamics, potential alternative stable states within the socio-ecological system. And there's been some research on this. One of the other questions I answered by text, and I was suggesting that there's this thing called the regime shifts database, which is looking at various different socio-ecological systems, how they've there's evidence of them reaching tipping points of regime shifts in ecological speak as a result of various different drivers. And there's a lot of interesting research in that area. In terms of specifically from climate tipping points, that research is still kind of ongoing and getting started. That's something that hopefully we'll do more of in this State of Tipping Points report, connecting the impacts of climate tipping points and seeing how that can kind of cascade through socio-ecological systems and what can be done to adapt to that.
Thank you. A question here being upvoted quite a bit. I'm still not clear of the effects of one tipping point being passed. Does it make the other tipping points more likely than the current graphs of possible likely shown in the presentation?
Yeah, so when I was presenting all those different thresholds, that they're all independently estimated for each tipping point by itself. I did talk a bit about in the background to do with interactions and potential cascades between climate tipping elements. But our estimates are not directly taking account into that, because we just wanted to be able to get a specific threshold range and estimates for each of those independently. It's very likely that interactions between all those tipping elements will change the likelihood of those tipping elements and change the thresholds potentially as well. But that was too much to tackle in one paper alone. It was already a bit of a stonker in terms of size. That's kind of like follow-up research to do. But I was involved in a paper published in December to do with how interactions in a particular tipping cascade, the one I showed down the Atlantic, how that interacts with different overshoot scenarios. So if we peak, for example, at 2 degrees and come back down to 1.5 degrees, how much more likely is a tipping cascade under that rather than just plateauing at 1.5. So we are doing that sort of research now, but yes, the results in my paper are specifically to do with each tipping point on its own, and it could change with further information about how they all interact.
Thank you, David. So Martin has asked, Saul Griffith in Electrify shows that relying on organic adoption is not enough to meet our adoption goals for EVs, heat pumps, electric stoves, etc. He says that we need regulation to enforce adoption in addition to incentives and technological progress. What is your opinion on this? What regulation or bans, if any, would you recommend? Lloyd, I'd be interested to hear. I think you touched on this in your discussion of subsidisation.
Yeah, absolutely. I couldn't agree more. And I think that's what we try and reflect in our framework around tipping points, is that those policy interventions, whatever form they take, whether it's a subsidy, a tax, or market shaping regulation, can create the enabling conditions for tipping points to take off. So we in our paper focus on a couple of different policies. Some are around mandates on green ammonia use, mandates on the share of car sales to be electric over time. And more generally, I think the one thing we really need to focus on at the moment that's really crucial is increasing the deployment of solar and wind by reducing planning and permitting timelines. So in the US, for example, the time it takes to approve a new solar farm has doubled since 2005. And in Europe, there is, at the moment across Germany and Italy and other European nations, there is more than 8 times more wind power capacity awaiting permitting and approval as we currently have in operation. So those timelines have got longer, and we need to bring them down if we want to really accelerate in time to have a fully decarbonised grid, which is the basis of everything else, the electrification of the rest of the economy and so on. A lot also needs to be done in heat pumps. It's much more complicated, I think, from a policy perspective, but I'm happy to sort of send some publications that look into that question in particular. And on the question of planning and permitting, the Energy Transition Commission has just published a very interesting piece of analysis on how we can reduce those planning and permitting timelines for solar and wind, which I would recommend.
Thank you. And we're getting close to the end, but I've pulled together 3 different comments around economic growth, which hopefully we can tackle together. So so are those learning curves showing the technologies only realistic in an ever faster growing economy, or are there constraints set by a slowing in economic growth as might occur in the future? And also, how do you think socioeconomic tipping points would look in models where economic degrowth would be considered? And should we not move away from growth for its own sake? We are on a finite planet, and the fixation on GDP has caused a lot of pollution and high emissions problems. So taking those questions together, how sort of integral is economic growth to those tipping points that you covered, Lloyd?
Yeah, I don't know if I'm going to have time in 4 minutes to cover growth versus degrowth. It's quite a big topic, but I mean, I would say, I think that you could see this whole tipping points agenda separately from growth. It will obviously contribute to growth, but there are a million different types of growth. Growth is starting to decouple from emissions very seriously in rich countries now. In the UK, for example, we've actually gone back down to our emissions per capita level. The last time we were so low was in 1879. So we are really starting to see the decoupling of growth and emissions. I think it's obviously it's still true that we need to focus on the good things we get from growth and not GDP as an end in and of itself. But a lot of the tipping points we're talking about will improve incomes and livelihoods by, for example, providing decentralized, cheap energy in areas of the world which currently don't have access to them. And if that's what growth looks like, then that's fine by me. I think we need to really go into the semantics of this question and understand that if it results in improved living standards, then that's something we should absolutely strive towards.
Thank you, Lloyd. Okay, we've only got about 2 minutes remaining, so I'd like to ask you to give a round of applause and thank our speakers for their excellent presentations and for fielding all of those fascinating questions that you were so kind to put in the chat. Many thanks to everyone online for your attention and participation today. I'd urge you to check out the other seminars in the series and also to attend the next event, which takes place on February 27th, which will focus on governance of climate tipping points. See the link in the chat. Many thanks again for your time, and hopefully see you again soon. Bye.
Thank you.
Thank you, everyone. Bye.